quick note before we get into it. Thanks for being patient with us, and sorry this episode is landing late on Thursday. We wanted to make sure this one was worth the wait.
Yeah, there was just a ton of ground to cover for this one.
Exactly. So, okay, I want you to imagine spending millions of dollars building just this flawless, mathematically perfect bank vault.
Right.
Like the steel is 3 feet thick, the biometrics are, state of the art, and the cryptography securing the lock is mathematically unassailable.
The ultimate zero trust system.
Exactly. A total zero trust environment.
Mm.
But then you take the master keys and you just hand them over to the guy who delivers your water cooler jugs.
Oh, man.
Just because, I don't know, he's been super friendly to you for the last 6 months.
Yeah, he asked about your kids, so you hand over the keys.
Right. And today we are unpacking how $285 million vanished.
Yeah.
And it wasn't through a shattered cryptographic firewall. It was literally through a friendly Telegram chat.
It's honestly devastating.
It is. But to really understand the irony of that exploit, we first have to look at the incredibly robust systems we are currently building to replace human trust.
Right, because the contrast is just jarring.
It really is. We're talking about the collision between these highly efficient, decentralized networks, AI agents that are, frankly, bizarrely wasteful.
Very wasteful right now.
Yeah, and the creation of portable machine selfhood, plus internet-native micropayments.
Because on one side, we have engineered this base layer infrastructure that processes global economic throughput with just ruthless mathematical precision.
Right.
And we are building decentralized identity protocols that give autonomous code a persistent, cryptographically verifiable existence.
Like machines having their own faces, essentially.
Exactly. We're even resurrecting dormant internet protocols to give these machines their own non-custodial economy. But then at the very tip of this highly advanced technological sphere, we still have, the human brain.
The ultimate legacy hardware.
Right. An inherently social, deeply exploitable piece of legacy hardware. So to understand where this whole industry is actually heading, we have to look at the friction between the flawless math we write and the messy operational realities we live in.
And there is literally no better place to see that flawless math in action than the live heartbeat of the infrastructure itself.
Oh, absolutely.
So we pulled the live Bitcoin network data literally today, April 9, 2026, using the mempool.space API.
Fresh off the wire.
Fresh data. During our prep, the chain tip was hovering right around block 944407. So to get a pristine, completely confirmed snapshot, we grabbed a window of blocks just slightly behind that tip.
Right, to avoid any edge case reorgs.
Exactly.
That's right.
Specifically, we looked at the 16 blocks from 944384 through 944399.
So we're looking at a slice of network history just, 8 to 23 blocks behind the bleeding edge?
Yeah, exactly. And in that tiny window, which ended at exactly 23.04.25 UTC today, the network processed 74,787 transactions.
Which is just a staggering amount of economic density for such a short window.
It really is.
But, the metric that truly illustrates the organic, sort of unpredictable nature of a decentralized network is the variance in the block discovery time.
Oh, the time gap, yeah.
Right. If we look at the gap between block 944398 and our anchor block 944399, it was incredibly brief.
It was, 31 seconds?
Just 31 seconds.
Which is wild, right? Because we both know the protocol targets a 10-minute average block time.
Right, the 10-minute heartbeat.
Yeah, acting as this steady metronomic heartbeat. But that 10-minute figure is just a statistical average covering up wildly erratic individual events.
That's a massive smoothing function.
Exactly. Because mining is fundamentally a probabilistic guessing game. It's like rolling a billion-sided die looking for a specific number of leading zeros.
Right.
You don't get a block on a neat, predictable schedule. It's a Poisson process.
Yeah.
The events are independent.
Yeah, every hash has the exact same probability as the last one.
Right. So you might sit there sweating for 45 minutes waiting for a single confirmation, and then a miner stumbles onto a valid hash just 31 seconds after the previous block.
And that Poisson distribution is really essential to understanding network health.
How so?
Well, it proves the mining process remains a memoryless brute force lottery, right? It's untampered by any central coordination. If blocks were arriving exactly every 10 minutes, we'd know the system was rigged.
Now that makes sense. A perfectly smooth line would actually be a red flag.
Exactly. But what's equally important in the specific window we pulled is the sheer payload being settled.
Right, the density.
Yeah, look at block 944394, which came in a bit earlier at 22.23 UTC. It packed in 7,756 transactions.
Over 7,000.
Right. Over 7,000 distinct economic actions bundled, hashed, and immutably settled in one single cryptographic payload.
Wow.
So this empirical data completely confirms the base layer infrastructure is highly active. It's carrying massive throughput without any degradation in consensus.
Right, the base layer is humming. But let's dig into a specific data point in that anchor block, 944399.
Okay.
Because I know it's going to make, like, casual Block Explorer watchers do a total double take.
I think I know what you're going to say.
The serialized size of that block, the one that arrived in just 31 seconds, by the way, was massive. It clocked in at 3,228,687 bytes.
Over 3.2 megabytes.
Yeah, over 3.2 megabytes. And for anyone who remembers the vicious block size wars...
Oh, the scaling wars.
Right, where developers fought tooth and nail over a strict 1 megabyte hard limit. Seeing a 3.2 megabyte block physically appended to the chain immediately raises alarm bells.
People panic. They think, okay, let's unpack this.
Yeah, I mean, 3.2 megabytes sounds huge.
Yeah.
Is the network breaking? Are we suffering from some kind of catastrophic bloat?
Right, and it's a very common visual anomaly that trips up observers when they rely solely on raw byte metrics.
That's not breaking.
No, the network is absolutely not breaking. That 3.2 megabyte figure is actually a masterclass in how miners maximize their revenue using the post-SegWit consensus rules.
Okay, break that down for us.
Well, we have to separate the concept of raw serialized bytes from the concept of block weight units.
Right, because segregated witness fundamentally changed the accounting system.
Exactly.
Before SegWit, blocks were strictly constrained by that physical 1 megabyte size limit. Every byte was treated equally.
Yeah, a byte was a byte. But the SegWit upgrade completely rewrote the math. It separated the transaction signatures, which is the witness data, from the core transaction data, like the sender, receiver, and amount.
Segregating the witness.
Exactly. So instead of measuring raw size, the network now measures weight, and it enforces a maximum cap of 4 million weight units per block.
4 million limit.
Right. And non-witness data is heavy. Every byte of core transaction data costs 4 weight units.
Okay.
But witness data, the cryptographic signatures, are heavily discounted. Every byte of witness data only costs 1 weight unit.
Okay, so miners are basically playing a massive high-stakes game of Tetris.
That's a perfect way to put it.
Because signature data is mathematically, like, cheaper in terms of weight. You can physically cram far more raw bytes into a block.
Right, provided the vast majority of those bytes are just signature data.
Right, exactly.
They're running highly optimized knapsack algorithms to figure this out in milliseconds, and block 944399 perfectly illustrates this.
How so?
Well, the serialized byte size is enormous at over 3.2 megabytes, but when you run the consensus math and calculate the actual weight, it comes in at 3,993,552 weight units.
Oh, wow. So they're right up against that 4 million cap.
That is practically scraping the paint off the 4 million weight unit ceiling.
That's incredibly precise.
It is. The miners are flawlessly utilizing the witness discount to pack the block to the absolute theoretical limit of the protocol. So, to your earlier point, it's not bloat.
It's peak optimization.
Exactly. It's peak optimization.
The juxtaposition here is incredible, though. Like, we have this battle-tested, hyper-efficient base layer running knapsack algorithms in milliseconds to optimize data down to the single weight unit.
Right.
The math is flawless. But, and here's the pivot, what happens when the automated agents, the sophisticated LM-driven entities that are increasingly trying to interface with this pristine infrastructure, actually hit the real world?
Oh, they crash and burn.
Yeah, because based on the Microsoft Aspire blog post published just 2 days ago, on April 7th, 2026, these brilliant AI agents are currently tripping over their own shoelaces in the most mundane ways possible.
Yeah. The post is titled Agentic Development Aspirations. Build, run, observe without more markdown.
Catchy title.
Right.
Yeah.
But it delivers a sobering reality check that this whole industry desperately needs to internalize.
What's the core argument they're making?
The core argument is that autonomous agents have achieved near brilliance at bounded tasks, like just generating code.
Generating syntax.
Yeah. But software engineering isn't just typing syntax into a text file. It's an operational loop.
Right, you have to actually run it.
Exactly. You have to build the application, execute it within the messy reality of a host operating system, observe its behavior, diagnose failures, and iterate.
The whole dev cycle.
Yes. And the moment these agents enter that operational loop, their efficiency just collapses.
Wait, let's be real about this for a second. We're constantly bombarded with benchmarks showing these frontier models passing the bar exam writing complex sorting algorithms in one shot, and basically ingesting the entirety of Stack Overflow.
I know, the benchmark hype is real.
If an LLM knows literally everything there is to know about Python, how on earth is it fumbling basic execution? Are we just making excuses for bad model architecture by blaming the environment?
No, it's not an excuse at all. It's a fundamental misunderstanding of what intelligence actually requires to be productive.
Okay, unpack that.
Intelligence is pattern matching and reasoning, right? But an operating system is an inherently chaotic, stateful environment.
Stateful being the key word there.
Exactly. The Aspire post explicitly highlights the mundane paper cuts that are destroying agent efficiency. Things like port conflicts, phantom processes, unset environment variables.
So like the infrastructure stuff.
Right. Imagine a developer agent generates a flawless web server script and tries to execute it, hard-coding it to listen on port 8080.
Classic.
Right. But a previous aborted test run of that exact same script crashed silently, leaving a phantom background process still clinging to port 8080.
Oh, I've had that happen. A human developer sees the terminal spit out address already in use.
Right.
They instantly recognize the state mismatch.
Right. What do?
You run a quick command to find the process ID, you kill the phantom process, and you restart the server. It takes like 5 seconds.
Exactly. Because you have context. But an agent lacks that overarching contextual awareness of the host machine's state.
It just sees text.
Right. It sees the error code, and because its primary interface with the world is code generation, it tries to solve an infrastructure problem with more code.
Oh, no.
Yeah. It might hallucinate a completely new networking library.
Oh, geez.
Or it might try to rewrite the entire routing stack, or attempt to reconfigure the firewall rules.
Just to fix a blocked port.
Yes. It burns massive amounts of API credits and compute cycles chasing a solution to a problem it fundamentally misinterprets, all because the environment it was dropped into was underspecified.
It's like hiring a brilliant architect who gets trapped in the lobby because they can't figure out how the security turnstile works.
Yes. Perfect analogy.
They know exactly how to design a skyscraper, they understand load-bearing physics perfectly, but they're just pushing on the pull door in the lobby until they pass out from exhaustion.
Exactly. They have the intelligence, but they lack the localized observability to apply it.
And that's why the Microsoft piece emphasizes this benchmark of useful work per cycle.
Right. Useful work, not just work.
Because right now, the AI space celebrates if an agent eventually completes a task. Like if you let an agent run overnight and it loops through 70 iterations of failed port bindings, crazy hallucinations, and environment errors before finally getting the app deployed at 4 a.m., people call it a massive success.
They post it on Twitter like a triumph.
Right. But the compute waste is astronomical. An agent's runtime is currently defined by friction.
It is. So throwing a larger model with, a trillion more parameters at the problem doesn't fix it.
Right. If the architect is still stuck in the lobby, giving him a bigger brain doesn't open the turnstile.
Exactly. The fix requires structural engineering, not just cognitive scaling. We have to build deterministic environments for these agents.
Deterministic meaning predictable.
Right. They need strict process isolation, unambiguous feedback loops, and structured observability into the state of the file system and network ports.
They need guardrails.
Exactly. Until the infrastructure matures to match the intelligence, these highly articulate models will just remain trapped in chaotic, unpredictable rooms.
And the core issue here is fragility, really, because an agent running a local script is a disposable entity.
Highly disposable.
If the terminal session crashes or the Docker container restarts, the agent's context is entirely wiped. It wakes up amnesiac.
It has no idea what it was doing.
Right. It has to rebuild its understanding of the task from scratch. So if we want these agents to actually coordinate, perform multi-step economic tasks, and survive the chaos of an operational loop, they need an anchor.
They need a thread of continuity.
They need a continuous thread of identity.
Right. They need portable selfhood.
Portable selfhood.
Yes. Which brings us directly to the W3C Nostr Community Group draft, detailing the Nostr DID, or Decentralized Identifier, method specification.
This is a huge shift.
It is a monumental shift in how identity functions on the network, specifically for autonomous actors.
Because we both know DIDs have been floating around the cryptography space for years.
Oh, yeah. Years.
But tying them specifically to the Nostr architecture feels like a major pivot. Right now, a machine's identity, or a human's for that matter, is almost entirely custodied by centralized platforms.
Right, you're renting your identity.
Exactly.
Mhm.
You authenticate via an AWS IAM role, or a GitHub token, or a Google Oath login. The platform grants you your identity.
And, more importantly, they can revoke it at their absolute discretion.
Just flip a switch.
Right. If the platform experiences an outage, or if your agent triggers an automated spam ban, that identity is instantly vaporized.
And all the work goes with it.
Exactly. The agent loses its permissions, its history, its routing information, and its capacity to coordinate with other agents.
It just ceases to exist.
Right. But the Nostr DID draft solves this by replacing platform custody with cryptographic math.
Okay, how does that work mathematically?
It uses raw SecP256K1 public keys.
Which is the exact same elliptic curve cryptography used in Bitcoin.
Exactly the same. It uses that public key as the durable identifier itself.
Here's where it gets really interesting for the listener. So the agent generates a private key locally. It holds that key in its own secure enclave.
Right, local.
The mathematical derivative of that private key, which is the public key, becomes its immutable name, its face, its permanent address on the web.
It grants the agent true sovereign continuity. No matter what host environment it is currently running in, or what API it is talking to, it can cryptographically sign a message proving it is the exact same agent that executed a specific job 3 days ago.
That is powerful.
It is. But an identity alone is just a static label, right?
Sure, it's just a string of characters.
Exactly. The genius of the Nostr DID draft is how it builds a multi-relay coordination mesh on top of that identity.
Okay, let's dig into the DID document itself, because a DID document is essentially a standardized JSON file associated with that public key, right?
Right, it's a metadata file.
It outlines how to interact with the entity. But this draft specifically incorporates relay service endpoints. How does that practically bridge the gap between a standalone public key and a robust, fault-tolerant coordination network?
Well, in the Nostr protocol, clients and agents don't talk directly to each other peer-to-peer. They publish and subscribe to independent servers called relays.
Right, it's a pub-sub model.
Exactly. If an agent only has a public key, other entities know who it is, but they have absolutely no idea where to send it data.
Because it doesn't have an IP address attached to the key.
Right. By embedding relay service endpoints directly into the DID document, the agent is effectively publishing its routing table.
Ah, okay.
It broadcasts, I am public key XYZ, and I am currently listening for instructions and coordination messages on these 3 specific relays.
So if a centralized server goes down, the agent doesn't just drop off the map?
No, the mesh architecture provides immediate failover.
That's huge.
It is. If an orchestrator agent is trying to assign a complex data analysis task to a worker agent and relay A crashes, the orchestrator simply checks the DID document.
It sees the backup relay.
Right. It sees the backup relays and seamlessly routes the payload to relay B. The coordination continues without relying on any central directory.
Okay, let's connect this back to our poor architects stuck in the lobby in the first section.
The wasteful runtime.
Yeah. We established that agents waste compute because their local environments crash or they get bogged down in port conflicts. Does having a SecP256K1 public key and a multi-relay DID document actually prevent an OS-level container crash?
Well, no, it doesn't prevent the local crash,
Okay.
but it fundamentally changes what the crash means for the broader system.
Oh, so.
It solves the state preservation problem. If a worker agent gets trapped in a court conflict loop and its local Docker container is violently killed by the orchestrator,
Which happens all the time.
its work history isn't lost anymore.
Because of the DID.
Yes. The orchestrator simply spins up a fresh, clean container. The worker agent boots up, uses its persistent private key to cryptographically re-authenticate its identity, pings the orchestrator over the Nostr relay mesh, and requests the last known state.
Oh, wow.
Right. The agent seamlessly resumes its task. We've transformed the agent from a brittle, disposable script into a persistent, immortal worker navigating a decentralized mesh.
Okay, so we've solved the memory problem. The agent knows who it is, other agents know how to route messages to it, and it can survive a catastrophic server failure.
Right.
But an immortal, highly coordinated agent is still functionally useless if it's broke.
True. It needs resources.
Exactly. If it hits an API wall that requires payment to process data, download a data set, or rent GPU compute, it can't just pause its execution loop and wait for a human operator to wake up and type in a 16-digit credit card number.
That breaks the whole automation cycle.
Totally. It needs internet-native money that operates at the exact speed of code.
The payment rail has to be as programmable, stateless, and autonomous as the agents themselves.
Right.
And honestly, for decades, payment has been the most cumbersome, archaic layer of the software stack.
He really has.
We can stream high-definition video across the globe in milliseconds, but facilitating a 5-cent transaction between two machines required a labyrinth of merchant accounts, payment gateways, and identity verification delays.
Which brings us to a massively significant engineering piece published by Lightning Engineering on March 11, 2026.
The L402 protocol.
Yes. They detailed the L402 protocol, framing it explicitly as the Internet-native payment protocol for agents. And what I find so elegant about L402 is that it isn't inventing a completely new esoteric standard.
No, it's looking backward.
Right. It's performing architectural archaeology. It's reviving a piece of the Internet's original scaffolding.
Yeah, when the foundational architects of the World Wide Web were designing HTTP status codes, they included codes we all recognize today.
Like 200 OK for success.
Right, or 404 not found, 403 forbidden. But they had the foresight to reserve a very specific, ambitious code, 402 payment required.
Which you never see.
You never see it. Their original vision was that the internet would naturally develop a native protocol for microtransactions, allowing browsers to seamlessly pay for content or services packet by packet.
But the protocol lay dormant for over 30 years.
Because the traditional financial system fundamentally cannot support internet-native micropayments.
Right, the fees.
Exactly.
Right.
A centralized credit card network can't process a 1-cent transaction without losing money on the interchange fees, let alone settle it instantly between two anonymous machine entities.
You couldn't detach a physical quarter to a TCP/IP packet.
No, you couldn't. So the 402 status code was basically an empty placeholder waiting for the right base layer.
And then came Lightning.
Right. The advent of the Bitcoin Lightning Network finally provided the required speed, finality, and near-zero cost structure. L402 takes that Lightning payment capability and ingeniously pairs it with token-based authentication.
Okay, let's walk through the actual cryptography and workflow of an L402 interaction for the listener. Let's say my Nostr-identified agent needs to run a complex query against a proprietary weather data API that charges, I don't know, half a cent per request.
Okay, standard use case.
My agent pings the protected endpoint.
Right.
What happens at the network layer?
The API server receives the GET request and sees there is no authorization header.
Because it's a first-time interaction.
Right. So instead of throwing a hard 403 forbidden, the server responds with the L402 HTTP challenge.
Okay.
Inside that response header are two critical components: a Lightning invoice for exactly half a cent and a cryptographically locked token known as a macaroon.
A macaroon.
Yeah, a macaroon.
So my agent receives this response, and because it's running a lightweight Lightning node or a non-custodial wallet integrated into its runtime, it parses the invoice and pays it instantly over the Lightning network.
Which takes milliseconds.
Right. And when the Lightning payment clears, the agent mathematically derives a cryptographic preimage.
Which is undeniable proof of payment.
Exactly. The agent then takes that preimage and combines it with the locked macaroon it received in the initial challenge. The math clicks together, unlocking the token.
Beautifully simple.
And then the agent instantly retries the original API request. But this time, it attaches the unlocked macaroon in the HTTP authorization header.
Right. The server inspects the header, verifies the cryptographic signature statelessly, and grants access. 200. Oh, okay. Boom.
The agent gets its data.
Yes. And the most brilliant part is that the server didn't have to look up an account in a database.
No database step at all.
None. It didn't check a credit card balance. It just verified the math on the token.
Stateless verification is the key to scaling machine commerce.
It's the only way it scales.
The server handles millions of agents without maintaining user tables or managing password resets. And these macaroons are highly flexible, right? An agent doesn't necessarily have to pay an invoice for every single query.
No, that would be inefficient.
An L402 token could be minted to grant access for 1,000 queries, or be time-locked to expire after 24 hours.
Exactly. And we both know macaroons have been utilized in authorization frameworks before, but applying their attenuation properties to L402 for autonomous agents is a massive paradigm shift.
Let's dig into that word, attenuation. How does that mathematical restriction actually play out when a lead orchestrator agent needs to spin up sub-agents? How does attenuation work without checking back with the central server?
Okay, so think of the standard authentication cookie as a dumb bearer token. Whoever holds it has full access.
Like a master key.
Right. But a macaroon is built on a chain of hash-based message authentication codes, or HMACs.
HMAC chain.
Yeah. This means a client can take a powerful macaroon, add a new limiting caveat like only valid for the image processing API or maximum spend of $1, and cryptographically hash that new rule into the token's signature.
So it's a programmable, self-filling prepaid card.
Yes.
If I give my lead agent a $10 master macaroon for an AWS service, and that agent delegates tasks to 3 disposable worker agents, it doesn't want to give them the master token.
Right, because a buggy worker might drain the whole $10 budget in an infinite loop.
Exactly.
Precisely. So the lead agent locally attenuates its master macaroon. It mathematically carves out 3 restricted tokens, each capped at a $1 spend limit.
Without asking AWS.
Right, completely offline. It hands these attenuated macaroons to the worker agents. When the workers hit the AWS API, the server hashes the caveats, verifies the HMAC chain against its original secret key, and grants access.
That is incredible.
The lead agent dynamically managed its own sub-budgets and permissions without ever contacting the AWS central server to create new IAM roles or API keys.
It bypasses the entirety of human-centric friction. No dashboards, no password managers, no identity verification.
It's just pure math.
We've taken payment, which historically was the most cumbersome bottleneck in the software stack, and made it as fluid and programmable as a standard HTTP GET request.
We really have.
So if we look at what we've discussed so far, we have engineered a flawless, zero-trust technological ecosystem.
The architecture is practically perfect.
We have a hyper-efficient base layer, settling dense cryptographic blocks in milliseconds. We have agents anchored by portable Nostr DIDs navigating a robust, decentralized mesh.
Right.
And we have L402 macaroons facilitating instant, mathematically verified, non-custodial machine commerce. It is a perfect trustless loop.
It is a profound architectural achievement. We have successfully removed the need for trust from the machine layer entirely.
And then a human being logs on.
Ah, yes, the humans.
Because for all our talk of perfect HMAC chains and decentralized mesh routing, the real world remains inherently messy, social, and deeply vulnerable.
It always does.
Which brings us crashing violently back to Earth with our final source today. Hackgrid published a staggering report today, April 9, 2026, detailing the $285 million exploit of the Drift protocol.
$285 million drained from a major decentralized finance platform.
It is a catastrophic loss of value.
It is, but what's fascinating here is, well, what demands our intense scrutiny today isn't the monetary figure, it is the exact methodology of the breach. It fundamentally challenges all our assumptions about security in decentralized systems.
Because when you hear about a $250 million DeFi hack, your mind immediately defaults to a highly sophisticated technical narrative.
You picture the Matrix.
Right. You picture a rogue savant sitting in a dark room, discovering a zero-day vulnerability in a smart contract. You imagine flash loan manipulation, a reentrancy bug, or some complex algorithmic arbitrage attack draining a liquidity pool.
You assume the code failed.
Exactly. But that isn't what happened here.
No, the code didn't fail. The protocol's math operated exactly as designed.
Which is the scary part.
Right. The Hackgrid report outlines that the attackers, who are widely attributed to state-sponsored North Korean cyber units, did not begin their campaign by brute-forcing cryptographic keys or probing smart contracts.
How did they start?
They began with the oldest, most unpatchable exploit in human history: social engineering.
Social engineering.
Yeah. They spent over 6 months executing a meticulous, long-con psychological operation against the Drift core team.
The anatomy of this long con is terrifying because of how mundane and familiar it is. This wasn't a misspelled phishing email from a Nigerian prince.
No, this was highly sophisticated.
The attackers fabricated a highly credible corporate identity, posing as a legitimate quantitative trading firm.
Right.
They recognized that the cryptographic perimeter was too hardened to assault directly, so they targeted the humans operating the perimeter. And they built trust using the exact same social rituals we all use in business.
Right, they didn't act like hackers. They acted like colleagues. They attended industry conferences.
Wait, really?
Yeah, they held regular professional video meetings with Drift developers. They engaged in constant friendly banter in private Telegram groups over a period of months.
Just blending right in?
Exactly. They slowly, deliberately established a narrative of partnership. They became familiar faces or avatars, rather, within the social layer of the Drift ecosystem.
And they understood that in the high-stakes world of crypto, Nothing buys legitimacy faster than capital.
That's the truth.
To solidify their facade as a heavy-hitting quant firm, the attackers actually deposited $1 million of their own controlled capital into a Drift ecosystem vault.
Just unbelievable.
I cannot get over the audacity of that move. They paid a $1 million entry fee simply to bypass the psychological defenses of the core team. It's an Ocean's 11 level social engineering con.
It is a profound manipulation of human heuristic biases. The human brain is wired to interpret costly signals as proof of alignment.
Right. If they risk $1 million, they must be on our side.
Exactly. The Drift team looked at the $1 million deposit, coupled with 6 months of friendly Telegram chats, and their brains automatically categorized these actors as trusted, heavily invested partners.
The social firewall was completely disabled.
Completely. And it was only after that trust was fully established that the attackers actually deployed their technical vectors.
Okay, let's outline those technical vectors, because they hit incredibly close to home for any modern developer. Once they were inside the circle of trust, how did they weaponize it to actually exfiltrate the funds?
Well, the report highlights several deeply concerning compromise paths. The first was a malicious test flight application.
Test flight for Apple beta apps.
Right. Test flight is Apple's standard platform for distributing beta versions of iOS apps. In the collaborative crypto space, sharing early builds of trading dashboards or wallet integrations via test flight is a daily occurrence.
Everyone does it.
Yeah. Because the attackers were viewed as trusted partners, when they casually offered a custom analytics tool to the Drift team, a core developer likely installed it without hesitation.
They bypassed all rigorous sandboxing protocols because they trusted the sender.
Exactly.
As a developer, the minute you trust someone, you inherently lower your security posture.
You let your guard down?
If an anonymous user sends you an executable file, you run it in a virtual machine or throw it away. If your partner of 6 months sends you a test flight link for a project you've been discussing, you tap install while waiting for your coffee.
It's muscle memory.
And the scary thing is, they didn't stop at test flight. The report mentions a compromised repository.
Right. In collaborative development, granting access to GitHub repositories is the ultimate expression of trust.
You're giving an external entity a direct pipeline into your code base.
By integrating a partner's library or approving their pull requests, the Drift team inadvertently introduced the vulnerabilities directly into their own infrastructure.
So they basically invited the vampires in.
Yes. But perhaps the most alarming vector detailed in the report relates to VS Code and Cursor.
Cursor, the AI-assisted code editor that has basically become standard issue for every developer writing smart contracts right now.
It's everywhere.
It deeply integrates LLMs directly into your local development environment.
Exactly. And while the granular forensic details of the exact payload are still emerging, the vector is clear. By exploiting the established trust relationship, the attackers were able to manipulate the AI-assisted development environment itself.
Wait, how?
They likely introduced malicious extensions, poisoned the local codebase, or manipulated the AI prompts to subtly alter the compiled code.
So the AI was helping them write the backdoor.
Exactly, creating the backdoor necessary to drain the protocol. They poisoned the well, but they were only able to walk up to the well because the human guards, completely blinded by social trust, literally held the gates open for them.
So we have to face the ultimate glaring contradiction of our industry. We spent the first 45 minutes of this deep dive marveling at the architecture of a zero-trust future.
We did.
We built portable cryptographic selfhood. We engineered stateless L402 macaroons. We deployed decentralized mesh routing that can survive a nuclear strike on a data center.
Mathematically flawless systems.
It is mathematically flawless. But how does all of that perfect zero-trust infrastructure protect you when your lead engineer willingly downloads a malicious binary because their buddy from a Telegram chat asked them to?
The brutal truth is that it offers absolutely no protection whatsoever.
None.
A mathematically perfect payment rail cannot stop an authorized user from signing a malicious transaction.
Right.
We are pouring billions of dollars of engineering talent into hardening the cryptography and isolating the machine execution environments, while the human brain, the ultimate administrative override, remains entirely unpatched and highly susceptible to basic manipulation.
It is a massive asymmetry. We are solving machine failure with math, but we are completely failing to solve human trust failure.
You can't patch human nature.
Better autonomous agents and faster blockchains do not magically delete social engineering.
Yeah.
If a human being with the private keys can be tricked, the entire zero-trust architecture collapses instantly.
You cannot solve human trust failure with better code. You can only solve it with unyielding process.
Right.
The industry must adopt a verification culture that completely overrides human vibes. It doesn't matter if an entity deposited $1 million.
It doesn't matter at all.
It doesn't matter if you had drinks with them at a conference in Dubai. If they send you a binary or if they submit a pull request, it must be treated with absolute, uncompromising zero-trust scrutiny.
Because the machines already operate this way.
Exactly. They don't trust each other's vibes. They verify the HMAZ chain. The vulnerability is strictly human.
Let's pull all these threads together, because the narrative arc we've traced today is critical for anyone navigating this space. Whether you are a developer prepping for sprint planning, an investor trying to separate AI hype from reality, or just someone fascinated by the evolving scaffolding of the internet, the lessons here are stark.
Very stark.
We started by examining the literal pulse of the decentralized base layer, watching miners flawlessly optimize 3.2 megabyte blocks using SegWit weight units in mere seconds.
Peak efficiency.
We then looked at the application layer, realizing that despite their intelligence, AI agents are currently incredibly wasteful when dropped into chaotic operating environments.
Tripping over phantom ports.
Right. And we explored the elegant solutions being built, giving those agents portable cryptographic selfhood through Nostr DIDs to survive server crashes, and equipping them with L402 macaroons to autonomously navigate a stateless internet-native economy.
We mapped out a perfect zero-trust machine ecosystem.
We did. Yet, as the staggering $285 million drift exploit proves with devastating clarity, as long as human beings retain override capabilities, as long as our psychology could be manipulated by 6 months of friendly chats and $1 million deposit, the system remains fundamentally, structurally vulnerable.
The tools are undeniably getting sharper, faster, and infinitely more autonomous. But the underlying lesson of the drift exploit is that human psychology remains the ultimate, unpatchable attack vector.
Which leaves us with a final lingering thought for you to mull over as you go about your week. We've established that human beings, driven by social impulses, are the weakest link in any security apparatus.
Without a doubt.
We've also established that machines, while currently struggling with operational friction, are being rigorously engineered to operate on pure, mathematically verifiable zero-trust principles.
Right.
So, if cryptographic identities become the standard and machine-native L402 payments become utterly flawless, but human trust remains permanently exploitable, are we heading toward a reality where the absolute safest entities to do business with aren't people at all?
That is a heavy question.
Will we reach a point where we prefer to transact exclusively with the very automated agents we currently view as wasteful, simply because an AI agent running an L402 check cannot be socially engineered over a 6-month Telegram chat?
They don't care about vibes.
Exactly. Will the ultimate security measure in decentralized finance be removing human vibes from the loop entirely, leaving a pure, cold mathematical economy?
It's entirely possible.
It is a wild, slightly terrifying thought. But after dissecting a $285 million heist built entirely on handshakes and manufactured trust, it might just be the logical conclusion of the technology we are building.
It just might be.
Thank you so much for joining us on this deep dive. We appreciate your patience with the schedule this week, and we're thrilled we got to unpack this massive collision of forces with you. Stay curious, verify the math, and we will catch you on the next one.